Welcome to improper integrals and indeterminate forms. So the general idea is if we're trying to find a definite interval, so for example, a definite integral from a to b of f of x dx, we can use the fundamental theorem of calculus. If, and this is a big if, f is continuous on the closed interval AB. So the question is, what if it's not? So what happens if it's not? So we get a few particular special cases of what we call improper intervals. And it turns out that we use limits to do our evaluating. So we use limits. So for example, if we have a vertical asymptote, so if we have definite integral from 0 to 1 of, say, 1 over x squared dx. Right? This is discontinuous at 0. We have a vertical asymptote at x equals 0. So what we're going to do is we wind up picking values that get closer and closer to 0 and taking those definite intervals and letting the limit go to 0. So it turns out that we set this as the limit as a goes to 0 from the right-hand side of the definite integral from a to 1 of 1 over x squared dx. So we have a limit involved. Another possible version we can have of these is if we have infinite bounds, which we have not yet seen with the fundamental theorem of calculus. I'm going to give myself a little more space quickly. So for another example, if we have, let's go definite integral from 1 to infinity of e to the negative x dx. Okay. So again, in this case, we're going on forever to the right. Right? So we're looking at that going on forever. Fundamental theorem of calculus, we're supposed to look at a closed interval, not an open interval. Once again, what we will do is we will pick a cutoff point, and then we will just let our cutoff point go to the right. So we will say this definite integral is the same thing as taking the limit as a goes to infinity of the definite integral from 1 to a e to the negative x dx. So we just see what the definite integrals approach as our bound goes to infinity. So again, both of these require limits. So both of these examples require limits. require evaluating limits. And are called improper intervals. I should just put this on the side. These two integrals here are referred to as improper intervals. They don't just magically fit our fundamental theorem of calculus. We have to use these limits to adapt. So since we are required to evaluate limits, we should do a review of the more complicated limits. So we are going to review the more complicated limits. Complicated limits. So these particular limits are indeterminate forms. So there are 7 cases where a limit is requires a fair amount of manipulation. To evaluate. And these are called indeterminate forms, which are limits that result in indeterminate forms. So these cases are 0 over 0. Right? In the 0 over 0 case, the numerator pulls to 0. The denominator pulls us to infinity, or plus or minus infinity. And the limit can be anything in between, or 0 or infinity. Similarly, we have infinity over infinity. Zero times infinity. So infinity over infinity, numerator is pulling us to infinity, denominator pulls to 0. 0 times infinity, same idea. Infinity minus infinity is another case. 0 raised to the 0th power, 1 raised to the infinite power, and infinity raised to the 0th power. The two different aspects are both pulling in opposite directions. Right? So all of these are being pulled in 2 directions. So all of these limits are being pulled in 2 directions, just like the 0 over 0 case. And it turns out that we can evaluate most of these limits using L'Hopital's rule. So we will be using L'Hopital's rule to evaluate limits that take an indeterminate form. So in the next, oops, I apologize. I need to update my screen. And we'll be using L'Hopital's rule to evaluate limits that take an indeterminate form. And so the next videos will cover L'Hopital's rule. Once we are comfortable with L'Hopital's rule, we will come back to improper integrals.